Good evening, everyone. Today we're going to be presenting about our project, which is Hybrid Quantum Classical Graph Generative Models to Target Alzheimer's Disease. I'm Linda.
I'm Nithya.
I'm Sahil.
And I'm Narasimhan.
And our advisor is Dr. McMahon. Okay, so as all of you know, drug discovery is one of the biggest problems in the world right now. However, it is very costly, both in terms of financial expense and time. So it can cost billions of dollars and takes 5 to 10 years just to generate one drug. Recently, computational methods have been used to speed up the research, in particular, machine learning models such as GANs, VAs, and GPTs. A GAN, or generative adversarial network, is basically where there's a generator and a discriminator, and the generator is trying to produce as good of fake data based off of the data set as it can. The discriminator is trying to discern which part is generated by the generator and which part is part of the actual original data set. So these two things basically work against each other, and the idea is that they both get better until the generator is generating data that can't be told apart from the original data set. In variational auto-encoders, inputs are encoded into what's called a latent space, as you can see in this graphic in the bottom right-hand corner. And then from there, you can sample different points on it to get data that wasn't necessarily originally encoded into it. And then finally, for GPTs, this you might recognize from ChatGPT, but it's basically a pre-trained model on a big data set, and it uses something called an attention mechanism to generate probability vectors, which will help with natural language processing. Just a little bit about our target disease, Alzheimer's. A lot of you are probably already familiar with it, but it's a progressive neurodegenerative disease with no known cure at the moment. And it's the most common cause of dementia, which is also better known as memory loss. Our goal is to design a model using one of these methods to generate potential drug candidates for Alzheimer's disease. And right now we're going to be going into a couple of our previously made models. These aren't specifically made to target Alzheimer's, but they are a baseline for our research.
Okay, so our first model was QGAN, or quantum GAN, and we trained the QGAN on the QM9 dataset, which has around 134,000 small organic molecules represented as XYZ files. And XYZ files basically contain atom vectors and sets of XYZ coordinates for each atom in the molecule, which makes it easy to visualize them. And it looks like the figures in the slide. The generator uses parametrized quantum circuits to generate atoms and XYZ files. And parametrized essentially just means that there are tunable parameters, or that specific parameters or angles can be changed. We use a simple classical neural network for the discriminator, as the discriminator is a lot less computationally heavy than the generator, and the task of basic classification is already very optimized in classical computing, so there wasn't a need to make it quantum. As for the results, we generated 300 molecules in total, of which 7 were considered chemically valid, which isn't a lot, but it shows that there's potential. Also, you can read our published JEI paper by scanning the QR code on the screen. So our second model was QNetGAN, and it's an upgraded version of QGAN that incorporates elements of NetGAN, a classical GAN that uses memory cells to generate graph-based data. LSTMs process data recurrently and are well suited for learning sequential data. Hence, they're perfect for GANs. As a result, our QNetGAN leverages the abilities of LSTMs to generate molecular graphs, which helps enforce atom connectivity, a problem we faced with the scattered atoms from before. While the classical discriminator still has the same task of binary classifications, it's also able to learn better from its mistakes via LSTMs. So thanks to LSTMs, QNetGAN demonstrates a 20 times increase in accuracy from 2.3% to 47%. However, our accuracy goal is 80% and more work needs to be done. So while the molecules generated by QNetGAN are connected, unlike the QGAN, most atoms are not connected according to the rules of chemistry. A few examples of the odd molecules QNetGAN has produced are a hydrogen atom forming 4 bonds, or an oxygen atom bonding to 5 other atoms, both of which are impossible. Also, our molecules don't have any double or triple bonds, and they don't form realistic cyclic structures and rings, and they look sort of like sideways houses. So we work to renovate these houses so that each atom satisfies the octet rule and makes them three-dimensional.
Okay, so moving on to our most recent model, QNetGAN. This is basically an upgraded version of QNetGAN without those problems. The new features that we added to this are GCN layers, also known as graph convolutional layers. They're specifically designed to work with graph data, and they're very good for working with chemical molecule structures, which is what we're trying to work with. So that's very suited very well. And then they combine with LSTMs to handle temporal graph structures. We also added a gradient penalty as well as an octet penalty. Both of these just help improve the results. The octet penalty is basically for chemical validity. So like if something like what's shown in this top graphic over here happens, like where a fluorine is connected to like 8 different things at the same time, that would be basically blocked out by the octet penalty because it doesn't satisfy the octet rule. And then for our results for this, we were able to generate 130 molecules, and out of those, 116 passed our criteria for chemical validity, which would make an 89% success rate, which is pretty good.
In this chart, we benchmark our various models. The NetGAN is the classical model. We didn't create it, but we did build off of it. It has a computational efficiency of 45 to 60 minutes, meaning that the model trains and reaches convergence in that time. Additionally, it requires around 8 gigabytes of memory. So although the accuracy is high, the classical model still uses a lot of resources. QGAN has a lower accuracy and uses more memory, but takes 30 minutes and has 120 quantum gates. 120 is a very high number of gates, and practically speaking would result in a lot of calculation errors if our model were to be run on a quantum computer. QNetGAN has far fewer quantum gates, making it more efficient, and only uses 3.4 gigabytes. Although its accuracy is at 47%, we plan to increase that with our research. QNetGAN version 2 has a very good accuracy, close to that of NetGAN, and it takes the least amount of time, at 9 to 10 minutes, and uses very little storage, at less than 1 gigabyte.
Okay, so a brief word about our molecular geometry optimization pipeline. This is basically a set of post-processing algorithms that we used on the generated molecules from our most recent version, which is QNetGAN v2. The Pinsky's rule of 5 is basically a test for how drug-like the molecule is, and it's basically a way to validate the molecules. We also use the octet rule and hydrogen addition algorithm, which I went over before, but those basically check and then add hydrogens accordingly to make sure that a molecule fits the octet rule. The formal charge algorithm is just to calculate the formal charge for each molecule, and then everything going on from there is basically how we make the molecules show up in 3D format. So we find their bond angles and lengths using databases and Perceptor theory. Then we see if they're cyclic or not. We find what molecular geometry they are, and then we create XYZ coordinates, essentially to put them in arbitrary spots in space to show where they are. And then at the end of this, we have more chemically feasible molecules.
So as Linda mentioned earlier, we now want to start targeting Alzheimer's disease. Alzheimer's disease is a neurodegenerative disease in which a person may face symptoms such as memory loss, concentration issues, mood swings, aggression, and a decline in motor skill at later stages. Alzheimer's is thought to be caused by a buildup of amyloid beta. The buildup of this peptide causes a disruption in cell communication, which in turn produces an immune response. This immune response is what actually causes the death of brain cells and the symptoms mentioned earlier. Next slide. So an important structure in the brain is the blood-brain barrier, which is a membrane that regulates the passage of molecules between the blood and the brain. For a drug to be effective in the brain, it must pass through the blood-brain barrier. The blood-brain barrier is composed of various parts. First part is the pericytes, which regulate blood flow and endothelial responses, and also regulates immune cell entry into the brain and the spinal cord. Next are the astrocytic end feet, which regulate the passage of nutrients between the blood and the brain, such as water and potassium ions. They help regulate metabolism. and helps the blood-brain barrier keep its structure. Another part is the brain endothelial cells, which help regulate the passage of molecules between the bloodstream and the brain, and shields the brain from toxins. Between these brain endothelial cells are the tight junctions, which have a high electrical resistance. They are formed by claudine, occludine, and other junctional adhesion molecules, or JAMs. They work with adherens junctions, which help stitch cells together to force molecules to be transported via the membrane and cytosol. This prevents molecules from leaking through the blood-brain barrier by moving around the cells. For a drug to be effective, as I mentioned earlier, they must be blood-brain barrier permeable. The permeability of a molecule can be predicted by molecular descriptors, which are values that encode structural and chemical properties of a molecule. Values that we have found to be effective at predicting blood-brain barrier permeability are the sum of topological distances between oxygen atoms, polar surface area, E-state topological parameters, and A log P3, which is a measure of hydrophobicity. These values can be used to verify if generated molecules are blood-brain barrier permeable.
One molecule with a lot of potential is the SMART antibody. Before the development of the antibody, mouse monoclonal antibodies were employed to reduce the excessive levels of amyloid beta and tau proteins found in the brains of those plagued by Alzheimer's. However, there was no cognitive improvement, most likely due to the fact that memory deficit was related to damage done before symptoms were observed, such as neuroinflammation or mitochondrial and lysosomal dysfunction. Therefore, a new heavy chain antibody called the SMART molecule was developed to target amyloid beta. It was injected into transgenic mice with Alzheimer's disease once weekly, and it was shown to have cleared amyloid plaque by about 60% compared to the control group. Now, the structure of the BBB is very important to consider when addressing the challenge of optimizing a molecule to get through it. There are three barriers to consider: microvascular endothelial cells, which make up most of the barrier, the blood-CSF barrier, which is between the blood and cerebrospinal fluid, and the arachnoid membrane. It's also important to note how the cells are arranged. Tight, gap, and adherens junctions all play a huge role in how molecules are able to get through the BBB. Tight junctions, which contribute to the BBB's selectivity, are especially important. So what impacts the permeability of a molecule through the BBB? Size, charge, structure, hydrophobicity, and affinity of a molecule are especially effectual, as large and hydrophilic molecules are restricted, but low affinity molecules perform better than those with a higher affinity. Because it's so hard to optimize a molecule to get through the BBB, mechanisms of antibody passage can be useful. For example, one of these is adsorptive-mediated transcytosis, or AMT, which relies on electrostatic interaction and cationization to enhance uptake into the brain. Another is carrier-mediated transport, or CMT, which uses specific carriers for small molecules, and another is receptor-mediated transcytosis, or RMT, which uses receptors for antibody transport. There are also structural modifications to possibly make to antibodies, such as minimizing the number of hydrogen bonds, glycosylation, which is the carbohydrate attachment to another molecule, using natural carriers, and perhaps cationization of the molecule.
So in this section, we're going to look at potential models that can generate molecules to penetrate the BBB. And a potential model is the mood model. It generates molecules by leveraging gradients from a property predictor. And the property predictor guides the reverse time diffusion process towards regions in the chemical space that are likely to yield high-scoring molecules based on target properties. The score of a molecule is just used to determine how unique the generated molecule is from the rest of the training set. High scoring means it's very unique or very different, and low scoring means it's similar to the training set molecules. The model is good for generating novel and specific types of drug-like molecules. So another potential molecular generation model is prompt smiles, which uses small strings to represent chemical structures. It essentially uses a process called scaffold decoration, in which a core molecular structure also known as a scaffold, is modified by adding various functional groups. This results in new potential molecules and can also use a process called fragment linking, in which smaller molecular fragments are connected to form a larger, more complex molecule. A model can link fragments to create chemical compounds with desired properties. After a molecule is generated, we use a benchmarking process to assign it a score based on drug-like properties.
Okay, so moving on to our next model, MOL-RL-MGPT. This is quite a lot of words and letters, so it stands for Molecular Reinforcement Learning, Multiple Generative Pre-trained Transformers. And this is just another model that we're looking into. It uses the GPT style transformer, which is shown here in this graphic over here that basically outlines the architecture of it. It's a set of attention layers, feed-forward layers, and then ending with the softmax activation function. It also uses reinforcement learning and has a diversification term to make sure that the molecules don't turn out similar to each other. So like how you saw in our QNetGAN one, where they were all like house-shaped, sideways houses, this model would not have it be like that. It would like make sure that all of the different molecules turn out differently from each other. It utilizes QED, JNK3, and GSK3B benchmarking systems. These are all just like sophisticated drug likeness tests. And then the original model was trained to target COVID-19. Our model, however, will be switching the target from COVID to Alzheimer's disease, and then we'll be implementing quantum versions of different parts of it, including a quantum softmax layer and quantum self-attention in order to hopefully increase the computational efficiency.
So next, we're going to talk about message passing neural networks, or MPNN. And these message passing neural networks can be implemented to predict blood-brain barrier permeability for a molecule. And it's basically a binary classification model, and it's a specific type of a graph neural network. And the reason it's different from traditional methods like random forests and support vector machines is that it operates on low-level graph features of a molecule instead of other properties. And it's hypothesized that this could yield better results, and implementations of this model have achieved high prediction accuracy.
This is the Guacamole benchmarking system, which is a system of benchmarking which allows models' performances to be compared to each other. This could be used to compare the different molecular generation models such as QSARs, QSPRs, phase, RNNs, GANs, and the other ones listed. It has two systems of benchmarking, one for generating molecules from a data set and one for generating molecules with specific chemical properties. For generating molecules from a data set, the benchmarks used are validity, uniqueness, Frechet ChemNet distance, which is a measure of structural and chemical similarity to molecules in the ChemNet database, and KL divergence, which compares the difference between the current and previously generated molecules. The benchmarks used for molecules generated via specific chemical properties are similarity, rediscovery, isomers, and median. Guacamole also has two algorithms that can filter out molecules that are unstable, reactive, or hard to synthesize. First is the high throughput screening, which is a brute force computation of the molecules. However, this is extremely computationally expensive. The other method is the Walters RD filtration system, which filters out molecules based on structural criteria. So for our future research, we are going to be building and comparing results from the new model types discussed and exploring new machine learning techniques and incorporating them into our models. We are also collaborating with Dr. McMahon's quantum chemistry group to build in molecular calculations into QNetGAN, and we hope to run our models on real quantum hardware. We recently submitted a paper in April of this year that was accepted for publication. However, a major point of feedback was to run our model on real quantum hardware to confirm the efficiency of our models. If we were to run our models on real quantum hardware, efficiency and resource usage are expected to improve significantly. However, we currently have issues with finding funding to run on quantum hardware.
Now, I'd like to thank our research advisor, Dr. McMahon, for his guidance through this project, Neil McMahon for helping us deal with server-related problems, Dr. New for his guidance on resources that we could utilize, and ASDRP for giving us the opportunity to conduct this high-level research and share it with you all. We would also like to thank the ex-QGAN and ex-QNetGAN group members, Ditanchu Sikdar, Arjun Bamra, Sathik Prasanna, Joey Huang, Adelina Chow, and Max Kui, and the quantum chemistry group for being amazing collaborators. To the right, you can find the QR codes for the references for this project, the JEI paper, and the IEEE conference proceeding. Thank you for listening, and let's open the floor for questions.